Hello everyone, welcome to this brief presentation of my thesis work. I hope that the topic will interest you as much as it interests me. As you can see in the small strip here on the right, it is a work on entropy and the second law of thermodynamics. I think that there are several aspects of its teaching that are problematic at the first cycle of higher education, and I will present here what these problems are and how I plan on getting rid of them in science education. First of all, a bit of context. What is entropy? It is an essential notion in thermodynamics, which is a branch of science that studies energy exchanges in which central notions are heat, work, and temperature. In this field, two major variables are defined, and you've already heard about them. Enthalpy, noted H, which is related to the internal energy contained in a system, and entropy, noted S, which interests us here. The way it's usually presented, and which, spoiler, is problematic, is that it's the disorder, the chaos of a system. The more energy a system has, the more enthalpy it has. The more disorder a system has, the more entropy it has. The way I rather choose to present it to you is like this. The entropy is the spread of energy, or even as engineers would call it, the quality of energy. Take for example the following diagram. At the top you have a hot tank in red, and at the bottom a cold tank in blue. Heat is allowed to flow from the hot to the cold tank via a machine that exploits the temperature gradient to produce useful work. In the end, we end up with two lukewarm tanks in purple. The entropy is greater in the lukewarm system. The energy is more spread out there. It is of a lower quality in the sense that you can no longer exploit the energy in a machine to produce useful work. Here are also three very important characteristics of entropy. First, it is specific to a system. We can say that one system has a high entropy and another system a low one, even if they have the same energy. Two, the entropy of the universe system always increases, whatever the process taking place in it. This is called the second law of thermodynamics. If the entropy decreases locally somewhere, it is because it has increased more elsewhere, and the total entropy of the universe has increased. Three, this is why we say that entropy defines spontaneity. When it increases, it signals a spontaneous process. This is also why it is linked to the arrow of time. Between two given situations, for which you don't have a chronology, it is always the situation with the most entropy that comes second. There are two aspects of the problem that I'd like to present to you: the macroscopic properties emergence from microscopic models, and the conflicts and conciliation between two historical models, the macroscopic one and the microscopic one. Indeed, this metaphor of disorder can be useful in some successful cases. For example, to explain the entropies of the states of matter, this metaphor works very well. On the macro side, particles are more disordered in the gaseous states than in the liquid states, and they are more disordered in the liquid state than in the solid state, which is what we observe on the macro side. The entropy of gases is higher than that of liquids, itself higher than that of solids. The image, the metaphor, works. On the other hand, for an equally important example, it does not work, even though it is of the same level of conceptual difficulty. Take one mole of each of the four first noble gases in four containers at same temperature, same volume. A person who only works with the heuristic entropy equals disorder will probably think that the molecules of the four gases are disordered in the same way, and therefore that the entropies of the four gases are identical. this is not correct. In this case, the solution lies in another property, less known and much less intuitive than disorder, which is that entropy depends on the mass of the atoms under consideration. This is a consequence of the model of the particle in the box. The mass of the particle influences the number of accessible energy states and therefore the entropy. Consequently, the entropy of krypton, the heaviest, is greater than that of argon, neon, or helium. And here I'm going to show you a first result of my research. When we give this precise question, to a group of chemists, pharmacists, and geologists in first year at university level, before a course in classical macroscopic thermodynamics, and that is the case in blue, that is before the course, we can see that the majority of students choose the third answer, which is that all the entropies are identical. Worse, we observe that after this course, the great majority of them choose the wrong option of identical entropies. What they were taught and the way it was done reinforced them in a misconception of entropy. During the 19th century, Carnot, Clausius, and Gibbs formed a classical theory, but not an atomist one. It functions without particles. It is this theory that is still presented in the majority of bachelor curricula. In 1877, Boltzmann proposed a statistical explanation of thermodynamics. By considering quantified interaction between particles, we can find the same quantities as with the approach of Clausius and Gibbs. The metaphor of disorder is therefore alone a transfer from the statistical method to the macroscopic method. Once again, the macroscopic method does not need the use of particles, though it uses a metaphor that does. This borrowing is a symptom of the coexistence of these two theories, and it raises some questions such as, if one borrows, as with the metaphor of disorder, shouldn't it be better framed and its limit well defined? Just a word about the pedagogical framework in which I work. It is the one of conceptual change, in which a misconception is any reasoning mobilized by the student which is not in accordance with the scientifically accepted concept. A misconception can be naive, it can be incomplete, it does not respect the boundaries of the theory it's using, or it's a misconception that can just be plain false. The conceptual change theory is a framework for observing and analyzing the ways in which students' conceptions coexist and evolve. And here are my research questions. By which answers and erroneous justifications do the misconceptions of undergraduate students in higher education about entropy and the second law of thermodynamics manifest themselves in multiple answers tests? And how are these misconceptions influenced by a general thermodynamics course based on the macroscopic model? These are the two questions. Here is a description of the method I used. I administered a test with 11 questions, including the question of the noble gases that you just encountered, to populations of bachelor students, including engineers, chemists, pharmacists, and geologists. The data you will see here are those of pharmacists, chemists, and geologists in year 1. There are 5 multiple answers questions and 6 multiple answers questions with justifications, which are analyzed qualitatively afterwards. The questions have been created to make misconceptions arise. A test is administered before and after the course to see what effect the course has had on the design, on the misconceptions, sorry. Here are some results from the definition question, that is what we call it. On the left, the question asked is, entropy is ... with several items to tick. A temperature, a form of energy, a thermodynamic quantity, a state function, a reaction rate, a system property, or a process. On the right, a graph showing the results of a population of about 100 pharmacist chemists in year 1. In pre-tests, that means before the course, at this stage of their curriculum, the students have already had a course in general chemistry, which talks about entropy, and they have already made numerical calculations about them. In orange, the items with the wrong answers, such as entropy is a process. And in green, the correct items, such as entropy is a thermodynamic quantity. You can immediately notice 3 important results indicated by the arrows. Indicated by the red arrow, the misconception entropy is a form of energy is present in 48% of the students. This is a lot given the importance of the distinction between the two in classical thermodynamics course. Of the qualitative answers obtained to justify this misconception, some spoke of the fact that entropy was a form of energy as would be electrical energy or potential energy. Then indicated by the blue arrows, we notice that only half of the students select the correct items. Entropy is a system property and entropy is a state function. These are therefore 2 characteristics of entropy that are not well known by the students. We have analyzed textbooks and courses to try to understand this, and we suspect that this lack of knowledge is rooted in the fact that the macroscopic approach favors the process over the property. Teachers will talk about entropy variation, not entropy as such, which suggests that entropy is something that is attributable to an evolution, not a property. Let us now observe these 4 items in their evolution between the pre-test and the post-test of a classical thermodynamics course. The course has a positive effect on the energy item, but still, 1/3 of the students have an important misconception. One can suspect the misunderstanding of the fundamental formula ds equals dq reversible over T, which the students may interpret as an equality between heat and entropy, thus energy and entropy. We will pursue this reflection in future semi-directed interviews with students. The thermodynamic quantity state functions items are improving. They are precisely very important in the macroscopic approach, so this could be expected. The course has had a negative effect on the property item, which, as I have explained, is not an aspect that is strongly emphasized in a classical thermodynamics course. For example, we will ask in exercise to calculate the difference in entropy between reagents and products to predict whether the reaction is spontaneous or not. We will not ask what is the entropy of the products or that of the reagents. What should you remember of this presentation? There is a major conflict between the macroscopic and the microscopic approaches. Often, chemistry students are introduced to the macroscopic method first, with unjustified borrowing from the microscopic method in the presence of the disorder metaphor. And then they study the microscopic statistical approach in a later course in statistical physics. This poor collaboration between the 2 models, this bad mixing, is identified as a source of misconceptions. Our results show that a classical macroscopic thermodynamics course does not necessarily improve the misconceptions and does not necessarily reinforce the correct conceptions. The next steps in our study will therefore include a better joint explanation of the 2 models, perhaps by improving the metaphor of disorder, such as adding the notion of movement quantity disorder, or by better limiting its use and its relevance, or perhaps by proposing new methods of explanation. A review is in progress. From there, we will construct a new didactic approach to entropy, which will also make use of pedagogical devices that can more easily implement the new ways of explaining entropy, such as labs or simulations. Thank you very much for your attention. I hope this has given you interesting pieces of information, and I look forward to hearing feedback during our discussion.